Car enthusiasts might have heard this before. What takes the most time when building a car? You can split car manufacturing into thirds. The first third is body production. The second is paint. The third is assembly. The most time and energy-consuming part is the second one, the paint process. More specifically, the drying stage takes the largest share. Applying wet paint evenly, without defects, and then drying it uniformly under perfectly controlled conditions is extremely difficult and time-consuming. Interestingly, batteries face a very similar challenge. Drying consumes a tremendous amount of resources. In an electric vehicle, the battery accounts for roughly 30 to 40% of the vehicle's total cost, and a significant portion of that cost comes from the drying process. So, what if we could eliminate drying altogether? The battery manufacturing process broadly consists of raw materials, cell manufacturing, and pack assembly. Among all stages, cell manufacturing has the greatest impact on both cost and quality. Within this process, the most critical step is making electrodes. Currently, most battery electrodes are produced using a wet electrode process. Let's walk through how it works. First, 3 powders are prepared: active material, conductive additive, and binder. The active material stores lithium ions. The conductive additive enables electron flow. The binder acts as the adhesive that holds everything together. These powders are mixed with a solvent to form a thick liquid called slurry, which is then thinly coated onto a current collector, such as copper or aluminum foil. And this is where the real problem begins: drying. Because the slurry contains organic solvents like NMP, it must be completely evaporated by heating at temperatures above 200 degrees for extended periods of time. This step consumes a substantial amount of time and energy across the entire electrode manufacturing process. After drying, the electrode is roll-pressed to increase density and then cut to the desired size. However, this drying step limits manufacturing efficiency in several ways. First, it creates a process bottleneck. Drying takes so long that it slows down the entire production line. No matter how fast the coating step is, everything gets held up waiting for drying to finish. Imagine a hair salon where all customers are done shampooing, but there's only one hairdryer. Second, high energy consumption. Maintaining high temperatures for extended periods requires a large amount of electricity, which directly increases manufacturing costs. Third, environmental burden. Organic solvents like NMP emit volatile organic compounds. Catching and cleaning these emissions isn't free. It needs extra machines, extra energy, and the rules are only getting stricter worldwide. Fourth, capital investment costs. Drying equipment is large and expensive, occupying a significant portion of factory floor space, and both upfront capital investment and ongoing operating costs are substantial. Finally, quality variation. Factors such as slurry viscosity, drying speed, and temperature differences make it difficult to achieve consistent electrode quality. At a high level, these challenges closely resemble those found in automotive drying processes. So, how does the dry electrode process address these issues? Subscribe and follow along. In theory, it's very simple. The dry electrode process produces electrodes without using any solvent. Powdered active material and binder are dry mixed and then directly compressed into an electrode sheet. In other words, there is no slurry and no drying step at all. Because there is no need for solvent drying or recovery equipment, both equipment investment and even building construction costs can be reduced. More production lines can be installed within the same factory footprint, leading to significant cost savings across the entire battery manufacturing process. According to one research paper, manufacturing using the dry method eliminates toxic solvents, reducing energy consumption by approximately 46% and lowering production costs by up to 19%. These characteristics highlight the potential of dry electrodes as an environmentally friendly battery manufacturing approach. That's not all. Dry electrode processes may also increase battery energy density. Energy density improves when electrodes are thicker and denser. In conventional wet processes, however, coating thicker slurry layers can cause a phenomenon known as migration, where conductive additives and binders move toward the top during drying. This disrupts the conductive network between active material particles, reducing electrical conductivity. In contrast, the dry electrode process is formed entirely in the solid state. This makes it easier to produce thick electrodes while maintaining uniform distribution of binders and conductive additives throughout the structure. As a result, the proportion of cathode and anode material can be increased, while the usage of separators and current collectors can be reduced, ultimately improving energy density. This is a clean summary table comparing the wet and the dry process. Feel free to pause the video and take a closer look. But does simplifying the process compromise quality or performance? In the wet electrode process, the slurry penetrates the electrode surface, allowing particles to naturally arrange themselves. During drying, microscopic pores form, which serve as pathways for lithium-ion transport. Dry electrode process, on the other hand, is produced by compressing powders, resulting in a denser and more uniform structure. However, if the structure becomes too dense, lithium-ion transport pathways may be insufficient, and if compression is uneven, interlayer adhesion may be weakened. Early dry electrode coating technologies faced issues such as electrode delamination during repeated charge and discharge cycles due to insufficient interlayer adhesion, as well as performance variations caused by non-uniform ion diffusion paths. Thanks to recent advances in binder technology and powder processing, many of these issues have been significantly mitigated. To enable dry electrode processing, several key engineering challenges must be addressed. The most critical factor in dry processing is the binder. Traditional PVDF binders are optimized for wet processes, where they form slurries together with organic solvents. As a result, there's a fundamental structural mismatch with dry processes that don't use solvents at all. This makes it necessary to develop specialized binders that can provide strong adhesion and electrochemical stability even in a solid-state environment. Powder flowability is another crucial factor. When flowability is poor, achieving uniform mixing becomes difficult, and quality inconsistencies can occur during the compression stage. Addressing this challenge requires advanced process control technologies, such as modifying powder surfaces, optimizing particle size distribution, and precisely controlling humidity and temperature. In the roll-to-roll process used to compress electrodes, the combination of three variables is critical: pressure, temperature, and speed. If the pressure is too high, the electrode becomes excessively dense, making ion diffusion difficult. If it is too low, adhesion strength weakens. Temperature also plays a key role. If it is too high, the binder can degrade. If it is too low, proper adhesion cannot be achieved. And what about speed? Too fast, and uniformity suffers. Too slow, and productivity drops. Optimizing these three variables is the key to scaling dry electrode manufacturing for mass production. Currently, global battery companies, including Tesla and LG, are introducing dry electrode coating technologies in pilot lines or early-stage mass production, while some materials companies are developing binders and mixing equipment specifically optimized for dry electrodes. With pilot production ramping up, dry processing is no longer just theory. It's becoming a real-world alternative. Battery breakthroughs may not come only from futuristic materials, but from changing how batteries are made. Do you think dry electrode process can become the new standard for battery manufacturing? Share your thoughts in the comments, and don't forget to subscribe and like. We will be back with more trend-driven battery insights.